All right. So yeah, so the pion at rest decays to a muon and a neutrino. Find the energy of the outgoing muon in terms of the two masses m pi and m mu. Assume m nu is equal to 0. So first we write down the conservation of energy. Write down the conservation of energy. Right? The total energy E mu plus E nu is equal to E pi, right? Because it's a pion which is at rest decaying into a muon and a neutrino, right? And we know that E pi, because we have said that the pion is at rest, so this is m pi c square. So we have got this E mu plus E nu equal to m pi c square, and E mu is equal to m pi c square minus E nu, right? Now what do? We make, so now we know that E nu, right, the neutrino energy, right, the neutrino energy is P nu C, right, because it's massless. So we use that here. Okay. We also use the fact that okay. So we also use the fact that the momentum is conserved. All right. We also use the fact that the momentum is conserved. So P mu plus P nu has to be 0 because the particle was at rest initially in the reference frame that we are talking. We are looking at it. So P nu is equal to minus P mu, or P nu, the magnitude is the same, right? And so we can use, instead of P nu, we can use a P mu here, right? That's what we have done. Okay. And we know that right now we use this very useful relation that if the energy is known, what energy and mass are known, we can get the momentum, right? So now it's the matter. Now we got the equation that we need. It's a matter of solving for E mu. So we used energy conservation, we used momentum conservation, and from there we got P mu is equal to P mu. Okay, and then we used this important relation. Now we have got an equation which you can solve for E mu. That part is trivial, right? Okay. Now there's also this question as part of it. What's the velocity of the muon? Right. So we solved this problem and we got the result. These steps are a bit lengthy, but finally we got this result. E mu is equal to m pi square m mu square c square divided by 2 m pi. Okay. Now the next question is to find the velocity, right? I think we already started finding the velocity. Oof. Give me a moment. I think I closed. Okay, can you see the screen?
Yes, sir.
All right. Now, in order to find the velocity, the easiest way is to write. We know that E is equal to gamma mc square. All right. So we have already found out the energy of the muon. So we write it as gamma mc square, and we know gamma, right? You can square on both sides and then solve for V. Okay. That's a simple matter. There's no problem there, right? It involves a few steps, and in the end, you'll get this answer. Okay. Just square on both sides and solve for V. And you see that V is equal to C multiplied by m pi square minus m mu square divided by m pi square plus m mu square. Right now we are just learning to use the traditional way of equating the energy on both sides and the momentum on both sides. So that's what we are doing now. Sometimes there are easier ways to do that, but now we'll study this traditional way. It may be lengthy, but it's fine. We can do it like this. So this problems can be done like this. And again, these kinds of problems are asked in the NET exam, all right? But may not be exactly from the classical physics part, or maybe they ask it from particle physics part, or maybe from electrodynamics part. But these questions are being asked, all right, using energy conservation and momentum conservation, right? So I thought we can discuss them anyway because we studied special relativity. We can discuss them here, right? So this will be useful. Okay, may not be exactly from classical physics part, but such questions are being asked. Okay? So let's do another problem now. So here is the problem. A particle of mass m, right? Particle of mass m, okay, whose total energy is twice its rest energy. Total energy is equal to twice its rest energy. Rest energy collides with an identical particle at rest. Okay, collides with identical particle. This is particle 1, this is particle 2. It's identical, which means it has the same mass, which is at rest. All right. If they stick together, what's the mass of the resulting composite particle? What's its velocity? All right. So the question is this: mass and velocity of composite particle. The mass and velocity of the composite particle. All right. So this is not very difficult. All right. We'll see how to do. And one way to do this. All right. Here you get this information. M. The mass is m and the total energy is twice its rest energy. All right. One way to do this is that you can take E is equal to, okay, we know that E is equal to gamma mc square, right? Okay, and they have given that this is twice its rest energy. Mc square is the rest energy. Mc square is the rest energy, right? So we have got a particle with mass m colliding with a particle with mass m at rest. All right, and they stick together. What's the mass and velocity of this thing? That's the question. All right. So one way to do this is to write E is equal to gamma mc square, and then you can solve this to get velocity, and then you can find the momentum, etc. All right, because gamma is equal to 2. Gamma is equal to 2. You can try this method at home. All right, you can try this. I hope it's clear, right? Because E is equal to gamma mc square. Gamma is, it's said that the total energy is twice its rest energy. So we know that gamma is equal to 2. Okay. So using this, you can solve the problem. You may have to square and you have to square and solve for V, and then you can find gamma mv, etc. All right, these things are easy. But there's an easier way to do this. If you start doing this, you'll see that there are a few steps involved. All right, it becomes a bit lengthy. The calculation may become complicated. All right, so you can try this at home. Okay, this is not very difficult, but it involves more steps. Okay? An easier method is to use the relation. All right, is to use the relation. We have this relation: E square minus P square C square is equal to M square C raised to 4. Right, we can use this relation. Okay. So using this relation, you can find the momentum of the incident particle. You can find the momentum of the incident particle. Right. So you see that P1, we'll write it as particle 1. Okay. P1 C square, okay, is equal to right, E1 square minus M square C raised to 4. Okay, so that's equal to we know that this E1 is twice its rest energy. So energy is twice its rest energy. So you square that, and M square C raised to 4. Okay, so that's equal to 4 M square C raised to 4 minus M square C raised to 4. That's equal to 3 M square C raised to 4. Okay, what is this? This is equal to P1 square C square. Okay, that's equal to 3M square C raised to 4. Right, so you see that you easily get the momentum as P1 is equal to square root of 3 MC. Right, this is the quickest way to get the momentum because the energy is given. We know the mass. All right, this is the quickest way to find the momentum. Right, you can try this method. This also works. There's nothing wrong in doing this, but you will see that it involves more steps and it steals your time. Okay, so this is the quickest way to do this. Right, so we also know that P2 is equal to 0 because we said that the second particle is at rest. Okay, is this clear? Now we are ready to use the energy conservation equation, all right? Because we know that now E3 has to be equal to E1 plus E2, right? E1 is given, it is 2 mc square. Right? Particle 2, right? Particle 2 was at rest. So its energy is, we'll write it like this. Okay. E3 is equal to E1 plus E2, right? So that's equal to 2 mc. We can write it like so. Sorry. We say that E3 is equal to what was E1? This is energy conservation, right? We write down the equation for energy conservation. Okay, energy conservation says that E3 has to be equal to 2 mc square. This is the energy, total energy of this particle, right? It's given us twice the rest energy. So 2 mc square plus the total energy of this particle. This particle is at rest. So this is mc square. So this is simply 3 mc square. Okay, 3 mc square. Okay, what about the momentum of the third particle? That's equal to P1. Okay, plus P2, right? We assume that they are in the same direction, etc. Because one of them is at rest, only this has the direction, and in the end, the direction will also be the direction of mass 1. Okay, so P1 plus P2, so that's equal to, we have got P1 as square root of 3 mc, got square root of 3 mc, okay, plus P2 was 0 because that particle is at rest. Okay. Okay, all right. Now, what do we have to find? What have they asked? We have written down the energy conservation and momentum conservation. We know the energy of the third particle. We know the momentum of the third particle, right? You see, we know the energy and we know the momentum, right? We are asked to find the mass, I think, right? What's the mass of the composite particle and what's its velocity, right? So what's the mass? How do you find the mass? Again, you can use the energy momentum relation because you know that E square is equal to P square C square plus m square c raised to 4, or we are given the energy and the momentum. So you can find the mass like this. Okay, so you can find the mass like this. M square c raised to 4 is equal to E square minus P square C square, right? And we already have E and P. We already have E and P. This is, so this is equal to 9 m square c raised to 4 minus P square C square is 3 m square m square c raised to 4 because it's P square C square, right? So that's equal to 6 m square c raised to 4. In other words, you can cancel this c raised to 4 and c raised to 4. You see that, okay, I should have written a capital M here to distinguish it from the other thing, right? This is the small m. So you see that M is equal to square root of 6 multiplied by the initial mass, right? This is the simple answer to the question, right? So it may look a bit difficult when you see the question, but once you write down the energy and momentum conservation and find out what we can find, the answer is quite easy. You see that it's equal to square root of 6m. Is this clear?
Yes, sir.
Okay. Right. If something is not clear, we can ask. Right. We have done very simple thing. We found the total energy of the outgoing particle. We found the total momentum of the outgoing particle. Okay, that's all we did. Okay. So we calculated this P1 using, we already knew the energy of the first particle and the mass of the first particle because we need to find the answer in terms of the mass, right? So we used this energy momentum relation in order to calculate this, and again we use the energy momentum relation here to find the mass of the outgoing particle, okay, in terms of the mass of the incoming particles. All right. So both these particles had mass m. So you see that it's root 6 mass m. Okay. So what happens here? You see that it's again greater than, right? It's again greater than one of the masses. Okay. So yeah, you see that mass itself is not conserved. We again see that mass itself is not conserved. All right, because it can get converted into energy and vice versa. Okay. Now we need to find the velocity. We need to find the velocity. Sometimes this alone can be asked. All right, the momentum will be given, the energy will be given, and they'll just ask you to find the velocity. How do you do this? You know that I've already said this. All right, P is equal to gamma mv. Okay, E is equal to gamma mc square. Right, so you see that you can divide P by E is equal to gamma, gamma will get cancelled, M will get cancelled, so this will be V by C square, all right? Or V is equal to P by E, okay, multiplied by C square, all right? This is one way to do it, okay? So we have all that we need here because we know the final momentum, all right? We know the final momentum, it's root 3 mc, so we can say that V is equal to, we know the final moment, it's root 3 mc. We calculated it here, divided by the total energy. Total energy is 3 mc square, all right? And multiplied by c square. So this is equal to, what do you see? This is equal to m gets cancelled. Okay, so the final answer is, there's a c here. Okay, so there's a c. Yeah, there's the c getting cancelled with this. So finally, you see that root 3 by 3 is 1 by root 3. So final answer is c by root 3. That's the velocity of the outgoing particle. Right. So we did it in an easy way after calculating the momentum and the energy. Right. So if the momentum and energy are given for a relativistic particle, you don't have to look anywhere else. All right. You just divide them. Divide the momentum by the energy, and then you can find the velocity easily. All right, so that's a very simple question. Okay, now all right, let's do one more. We'll do a few problems, and in the end, I'll give you some more tricks to solve these kinds of problems. All right, but if you don't learn those tricks, it's fine. This method it works. All right, you write energy conservation, you write momentum conservation, and find what you need to find. Okay, that's the simple, the straightforward way. All right, to do that. But if you really get used to it, you see that you can use some other things to find the answers more easily. I'll solve some of these problems using that method after this. All right, first let's do it in the traditional way. So a neutral pion of rest mass m. So we have got a neutral pion of rest mass m. Okay, rest mass m, and momentum is given. P is equal to 3 by 4 mc. The momentum is given. All right, this is a neutral pion of rest mass m and momentum 3 by 4 mc. Decays into 2 photons. It decays into 2 photons. Decays into 2 photons. Decays into 2 photons. Okay, one of the photons is emitted in the same direction as the original pion. One of the photons is emitted in the same direction as the original pion. Okay, and the other in opposite direction. Other in the opposite direction. So we have got this pion moving like this. Okay, and you see that one photon gets emitted like this, and one photon in the opposite direction. Find the energy of each photon. Find the energy of each photon. Okay. All right. So we can use here. Let's write down what we have here. We see that p pi vector. All right. The momentum of the pion we'll write as p pi vector. Okay. I think we should write it as a modulus here, because otherwise we may confuse the notation. Okay. So this is equal to 3 by 4 m pi c. This is given. This is a given thing. All right. And the mass is also given. Mass is also given, right? So we are given the momentum. We know the mass. What we do? So we need to use what we need to use. We need to use the energy momentum conservation of that. So we need to find the energy. And once the momentum is given, you can find the energy in this easy way because we know of this. This is a very useful relation, all right? E pi square is equal to, you see that it's equal to p pi square c square plus m pi square c raised to 4. Okay, so that's equal to, now we know these things, all right? I'll write it like this just to avoid confusion. So this is 9 by 16, okay, m pi square c raised to 4 plus m pi square c raised to 4. So that's equal to, we can write as m pi square c raised to 4 multiplied by 9 by 16 plus 1. Okay, so that is m pi square c raised to 4 multiplied by 25 by 16. It's 25 by 16. All right. Now you take the square root, just take the square root. Just take the square root. So you get modulus of p pi, or the momentum. Okay, that's equal to 5 by 4 m pi c square. Okay, that's the momentum. All right. Now we make use of the energy conservation. Energy conservation, right? We can denote the outgoing photons as A and B, all right? So the total energy of the outgoing photons, all right, EA plus EB, the product, all right, because the pion is decaying into 2 photons. This is equal to the energy we already found here. It is 5 by 4 m pi c square. Okay, and then the momentum conservation tells us. Momentum conservation tells us that, you see that PA, all right? So you have to write it like so, right? PA plus PB is equal to what was the momentum? Momentum is given as 3 by 4 m pi c, okay? M pi c. There is some vector here, but we'll make it as magnitudes, all right? So we know that these particles are going in opposite directions, all right? One particle is going that way and one particle is going the other way. There are only 2 possible directions, all right? And this particle also goes in this direction. The pion. The pion is moving like this, photon A is moving like that, and photon B is moving like that, all right? So we'll write it as modulus, okay? And the direction we can give with a minus sign, okay? Because these two are moving in opposite directions. Is that clear? Okay, so now you just write the magnitude. It will be 3 by 4 m pi c. Okay, all right. So from here, you see that we are talking about a photon, all right? We are talking about a photon. So what's the next step that we can do here? What's the next thing that we can do here? Any guess? You know, what should we do to solve this problem? What are we supposed to find? Find the energy of each photon. We need to find the energy of each photon. How do you do this? Any quick guesses? We have got these 2 equations, all right? These are the equations we have. This is energy conservation and this is momentum conservation, all right? Any quick guess as to how to solve this problem to find the energy of each photon? Any idea? Quickly. Can you hear me?
Yes, sir.
Yeah, how can we solve this? We've got one equation for energy, total energy, and one equation for total momentum, right? How can you solve this equation for the energy of the photons?
E square is equal to
Yes.
ഇക്വേഷനിലോട്ട് കൊടുക്കാൻ പറ്റില്ല ഡിവൈഡ് ചെയ്യാൻ
ഏതിനെ ഡിവൈഡ് ചെയ്യണ്ടേ?
ഇങ്ങനെ പറ്റില്ല. മൊമെന്റത്തിനെ എനർജി വെച്ച്
velocity.
All right, so there's one thing you need to remember. Again, to use the energy momentum relation, all right, we have got an equation for the momentum here, and we know that for a photon, all right, the energy is simply Pc, right, because it's p square c square plus m square c raised to 4, and m is equal to 0. Am I right?
Okay.
So Pa can be written as Ea by c, and Pb can be written as Eb by c. Am I right? Yes. So you see that this equation implies that
Yes.
Ea minus Eb, right, there's a divide by c here. I'll put it, multiply to the other side. So 3 by 4 m pi c square. Is that correct? Okay.
yes.
Now you have an equation for Ea plus Eb. You have another equation for Ea minus Eb, right? Now if you add this, you can eliminate Eb. You get 2Ea is equal to, right, you just add this. So that is equal to 8 by 4. It's 2. Right, 2 m pi c square. This means that the energy of the first photon is equal to simply m pi c square. That's quite simple. Right? This is one thing you had to remember. Okay, it's one thing you had to remember. Right, because for a photon, E is equal to Pc. Okay, so we get two equations connecting the energies. We have to find two energies, right? So we just solve these equations. Now we can substitute this here or here, all right, and find, you can substitute it here, for example, or here.
2 times E എന്ന് എഴുതിയെന്നെ സാറേ.
ഏതാണ്?
Negative 2 times of E എന്ന്.
2 times Ea. നമ്മളിത് രണ്ടും ആഡ് ചെയ്യാണ്.
Okay.
Okay, അപ്പൊ 2 times Ea, Eb plus Eb 0 ആവും. ബാക്കിയുള്ളത് 8 by 4 m pi c square. Am I right? So it's 2 m pi c square. Right, so Ea is simply m pi c square. Correct? Got it?
Yes, sir.
All right. Now you just substitute this back into this or that equation. Right? You can find Ea. You just substitute Ea here. Right? So you see that Ea by minus Eb is equal to 3 by 4 m pi c square. So you see that Eb is equal to Ea minus 3 by 4 m pi c square. You just use this equation. And you see that this is equal to m pi c square minus 3 by 4 m pi c square, and that's equal to 1 by 4 m pi c square. So these are the energies of the photons, m pi c square and 1 by 4 m pi c square. All right. Now the only way to get used to these problems is to just look at these problems more and more. All right. You just do more problems like this, and then you will get an idea about what equations we can use, etc. Right. Even if you don't know anything, just start by writing the energy conservation and momentum conservation and see if you can use some of the relations that you have used. All right. And if you play around a little bit, finally you'll come to the correct answer. Okay. Anything?
ഇനിയും പുതിയ ബുക്ക് എടുക്കാനേ ഉള്ളൂ.
എന്താണ്?
ഇല്ല, ഒന്നുമില്ല സാർ.
Okay. All right. So it's 8:27. I think the meeting will go on only up to 8:30. All right. So from the next class, for a few classes, the classes will only be 40 minutes. Okay. അടുത്ത ക്ലാസ് മുതൽ 40 മിനിറ്റ് വെച്ചായിരിക്കും കുറച്ച് ക്ലാസ്സുകൾ. ഓക്കെ.
ഓക്കെ, സമയം ഇത് തന്നെയാണോ സാറേ?
ആ, സമയം ഇത് തന്നെ അയക്കാം. മാറ്റണോ? എന്തെങ്കിലും ചെറിയ മാറ്റം വരുത്തണോ? വേണ്ടല്ലോ.
ഇത്തിരി കൂടെ രാവിലെ ആണെങ്കിൽ
നേരത്തെ ആക്കിയ കൂടുതൽ ആൾക്കാർക്ക് ബുദ്ധിമുട്ടായിരിക്കും. എല്ലാവർക്കും ഓക്കെ ആണെങ്കിൽ ആക്കാം, എനിക്ക് കുഴപ്പമില്ല.
വേണ്ട സാറേ, ഭയങ്കര മഴയാണ്. ഇന്നിവിടെ ഹെവി. അപ്പൊ രാവിലെ കഴിഞ്ഞാൽ മഴ കുറയുവാണെങ്കിൽ റേഞ്ചിന് കൃത്യമായിട്ട് കിട്ടും. വിഷയമൊന്നുമില്ല.
അപ്പൊ ഈ ഞാൻ സൂമിൽ ചെയ്യുന്നുണ്ട് ഇപ്പൊ 40 മിനിറ്റ്സ് ആണ് അതിന്റെ ടൈം ലിമിറ്റ്. സൂമിന് എന്റെ സബ്സ്ക്രിപ്ഷൻ ഉണ്ടായിരുന്നു, അത് അവസാനിച്ചു. ഇപ്പൊ അത് വീണ്ടും വാങ്ങാനുള്ള സാമ്പത്തിക അവസ്ഥ ഇല്ല. അപ്പോൾ
അത് ഓരോ മാസം നമ്മൾ മേടിക്കണ്ടേ അത്?
ഓരോ മാസവും പേ ചെയ്തുകൊണ്ടിരിക്കണം.
ഉം.
അപ്പൊ പിന്നെ ഇനി ഞാൻ ഗൂഗിൾ മീറ്റിൽ സ്റ്റാർട്ട് ചെയ്തിട്ട് റെക്കോർഡ് ചെയ്യാനുള്ള സംവിധാനം ഉണ്ടാക്കുന്നതായിട്ട് സൂമിൽ തന്നെ 40 മിനിറ്റ്സ് ക്ലാസ് കണ്ടിന്യൂ ചെയ്യാം.
ഓക്കെ സാർ.
ഓക്കെ, അത് കഴിഞ്ഞ് ഗൂഗിൾ മീറ്റിൽ റെക്കോർഡ് ചെയ്യാനുള്ള സംവിധാനം ഞാൻ റെഡി ആക്കുന്നുണ്ട്. അത് കഴിയുമ്പോൾ നമുക്ക് വീണ്ടും യൂഷ്വൽ ഇതിൽ പോകാം. ഓക്കെ
ഓക്കെ സാർ.
അപ്പൊ വേണേ 2 മിനിറ്റ് കൂടെ നമുക്ക് നോക്കാം. ബട്ട് ഐ തിങ്ക് അറ്റ് 8:30 ഇറ്റ് വിൽ ബി ഓവർ. ഓൾറൈറ്റ്, വിൽ സീ. ഓക്കെ, ഇനി ഞാൻ വേറെ എന്താണ്
ഞങ്ങളെ കേറാൻ താമസിക്കുന്നോണ്ടായിരിക്കും. നാളെ കൃത്യസമയത്ത് കയറാം സാർ. അപ്പൊ 40
കൃത്യസമയത്ത് നമുക്ക് 40 മിനിറ്റ് കിട്ടും.
ഇപ്പൊ ഞാനൊക്കെ വന്നപ്പോ 5 മിനിറ്റ് ലേറ്റ് ആയി.
അതെ,
സോറി സാർ.
നിങ്ങൾ രണ്ടാളിപ്പോ വന്നിട്ടുള്ളത്.
ആദ്യം കേറാൻ ശ്രമിച്ചായിരുന്നു സാർ. അപ്പൊ
റേഞ്ച് ഉണ്ട് സാറേ, അത് ഇച്ചിരി
പറഞ്ഞു അത് കേറാൻ സാധിച്ചു. ഞാൻ ആദ്യം കേറാൻ ട്രൈ ചെയ്തായിരുന്നു. അപ്പം ഹോസ്റ്റ് ഈസ് പ്രിപ്പയറിംഗ് മീറ്റിംഗ് എന്ന് പറഞ്ഞ് അലൗ ചെയ്തില്ല കേറാൻ.
ഓക്കെ ഓക്കെ, ഞാൻ കറക്റ്റ് 7:50 സ്റ്റാർട്ട് ചെയ്തത്. 40 മിനിറ്റ്സ് തികച്ച് കിട്ടാൻ വേണ്ടിട്ടേ. നേരത്തെ സ്റ്റാർട്ട് ചെയ്ത് അത് പോകുമല്ലോ. ഇനി നമുക്ക് അടുത്ത ക്ലാസ്സിൽ നമ്മൾ നോക്കാൻ പോകുന്നത് an easier way to solve this. All right, we'll make use of the fact that the four momentum, we'll use the four momentum relations. Next class I'll give you some tricks to solve these kinds of problems. It's okay even if you don't learn them. നമ്മൾ മുമ്പ് കണ്ട പ്രോബ്ലംസ് ആ രീതിയിൽ തന്നെ ചെയ്താലും മതി. But we'll make use of the four momentum relations. Okay, four momentum relations to solve these problems. All right, in an easier manner. Some of the problems can be easily solved using this method. All right, and then we'll just discuss the Doppler effect and then stop special theory of relativity. Okay, so it's a plan. 30 time limit illa andu. Shall we continue?
Okay, sir.
All right, so I want to do this problem again. All right, a pion at rest decays into the first problem that we did today. I mean, we discussed it, that the last problem that we did in the last class, or in the previous class. A pion at rest decays into a muon and a neutrino. The same problem, right? A pion at rest, it's given that this is at rest, decays into a muon and a neutrino. Okay. Find the energy of the outgoing muon in terms of the two masses m pi and m mu. It's the same question. All right, assume m nu is equal to 0. Okay. Now we solved this using the energy conservation and momentum conservation. All right, now there's another way using four momentum conservation. You can just directly write the four momentum conservation. Right, so I'll write the four momentum conservation like this. Okay, p pi is equal to p mu plus p nu. Okay, we'll use p pi is equal to p mu plus p nu, and we have to make use of the fact that p pi vector is equal to 0 initially. P pi vector is equal to 0 initially. Right, so when I write a vector here, it means that it's a 3 vector. Okay, without a vector, it means it's a 4 vector. Okay, that's the notation we are using. Okay, so these are 4 vectors. These are 4 vectors. Okay, and this is 3 vector. So we know that initially it's given that the pion is at rest. So we know that p pi vector is equal to 0. Okay. Now I'll just solve this first. So from here from here we can write p pi minus p mu is equal to p nu. No problem. I just put it together. All right. I'll explain why I did this. Now you square on both sides. All right. Square on both sides. Sometimes this is an easier way to do so. Right? So you see that p pi minus p mu, these are 4 vectors, okay, is equal to p nu square, right? And what's p nu square? This is the 4 momentum square for a massless particle. What's it equal to? P nu square is equal to? Quick answer. P nu square is equal to?
Square 6.
Yeah, so you have to remember this important thing, the 4 momentum square, right? We wrote it as p mu, remember? 4 momentum square is equal to m square c square, right? P dot p is equal to m square c square. Well, this was the invariant relation that we wrote earlier. We found it in one of the previous classes. This is important to remember. Okay, So this nu is not an index. Right? This is not this just means it's a neutrino. I'm not using an indices here, right? I'm not using index here. This means that it's a neutrino. So this is a 4 momentum square of the neutrino. Right? So that's equal to m square c square, right? But for the mass of the neutrino is 0. Okay, so this is equal to 0. Am I right? Okay. So here, this we can write as this is p pi square plus p mu square minus 2 p. All right, you have to be careful. Minus 2 p pi dot. Right, these are 4 vectors. P mu. All right, I'm just squaring this. So it's p pi square plus p mu square minus 2 p pi dot p mu. This is equal to 0. Fine. And what's p pi square? What is p pi square? Again, you use this relation, right? Yes, it is m pi square c square, right? M pi square c square. And this is m mu square c square, right? Okay. And this is 2 p pi dot p mu. This is a scalar product of 2 4 vectors. We need to be a bit careful here. So we write it as, I write it in component form. Okay. P pi dot p mu. Right. What are the components of p pi? The 0th component. We know that the time component is energy divided by c, and we have got p pi vector. These are the components, right? Right. Is this clear? I've used the fact that the 4 momentum p pi has components e pi by c. We already saw that the 0th component is e divided by c. Okay, and then the 3 momentum. Right, these are the 4 components. I'm writing in the component form. Okay, and we have got here p mu. Again, it's e mu by c, comma p mu vector. P mu vector. Correct. I've written it in component form. All right, components of the vectors. So this again, this is equal to m pi square c square plus m mu square c square minus 2. Okay. Now you need to take the scalar product. Right? How do we take the scalar product of 2 4 vectors? You have to be careful. It's the 0th component multiplied e pi by c multiplied by e mu by c minus p pi vector dot p mu vector. Am I right? Because we said that the square of a 4 momentum a dot b is equal to a0 b0 minus a vector dot b vector. Am I right? That's what I've used here. Right? And now we use the fact that p pi vector is equal to 0. This is equal to 0 because it's initially at rest. It's given that it's initially at rest. Okay, so this becomes m pi square c square plus m mu square c square. This is equal to 0, right? Minus 2. What is e pi c? E pi, because it's at rest, this is equal to m pi c square. Okay, so this becomes m pi c square by c. So it is m pi c, all right? And e mu by c. We don't know e mu, that's what we have to find out. Okay, that's equal to 0 because on the right hand side we had 0. Do you follow this? Got it?
Yes.
Right, so now this is easy. Now you just solve for e mu. Just solve for e mu. I think I did it correctly. All right. So if you solve for e mu, you see that 2 e mu. I'll say 2 m pi e mu is equal to m pi square c square plus m mu square c square. All right. Or e mu is equal to m pi square c square plus m mu square c square divided by 2 m pi. So this is the same result that we obtained in the previous problem, right? Earlier we used energy conservation and momentum conservation separately. Okay, here we used the 4 momentum conservation and squared on both sides. All right, and on squaring we made use of the fact that p nu square for a massless particle, the 4 momentum square is 0. Okay, and why did we write it in this form? Now I'll tell you why we wrote it in this form, right? So we knew that p pi is 0. We knew that initially this is equal to 0, right? Now by combining it in this form, we were able to eliminate this p mu vector, which is an unknown, right? We were able to eliminate this p mu vector, correct? Because p pi vector is 0, right? That's the reason why. That's the reason why we started writing it as p pi is equal to p mu plus p mu, right? Now we brought this p pi and p mu together. P pi minus p mu is equal to p mu, so that when you make the square of this, we could eliminate p mu vector, correct? Okay. I think this is easier if you get used to it, but it's okay if you don't do this. You can use the conservation thing, but this is much quicker. You will notice that this is much quicker. All right. Now, again, I'll do something else. What if the question is to find p mu vector, right? What if the question is to find p mu vector, right? Now, then we don't have to eliminate this p mu vector. Then we write this in this form, right? Then we write this in this form. Right? In order to find p mu vector, we'll simply write p mu is equal to, okay, we'll solve for p mu from here. So p mu is equal to p pi minus p nu, right? P mu is equal to p pi minus p nu, all right? Okay, now we'll make use of the fact that and now just try squaring this. Okay, you'll see that the answer comes out. Okay, so initially we did p nu is equal to p pi minus p mu. Now we are doing p mu is equal to p pi minus p mu. All right, so now if you square on both sides, you'll get the square of p mu square. P mu square is, we know that, m pi square c square, sorry, m mu square c square, m mu square c square. Okay, that's equal to p pi square is m pi square c square, p nu square is 0, right? And then you have this term 2 p pi dot p nu, okay, where these are 4 vectors. These are 4 vectors. Okay, so that's equal to m pi square c square minus 2. Now we write it in component form. We know that e pi is equal to m pi c square, right, divided by c, so that e by c. I'm writing the components, okay, comma p pi vector, that's 0. P pi vector is 0. Okay, and here you have got p, yeah, the components are, we can write as e nu by c comma p nu vector. Okay, now we are able to eliminate this p nu because this will give, okay, this is equal to m pi square c square minus, right, you just multiply these things, m pi square c square minus 2 m pi e nu, okay, the other term is 0 plus 0. This is m nu square c square, all right? So this is equal to m pi square c square minus 2 m pi. Now we make use of the idea. What is E nu? What is E nu? E nu is, because it's a massless particle, it's simply P nu C, right? It's P nu C. C. Okay, it's P nu multiplied by C. Fine. Now what is P nu? What is P nu? P nu, we know that, because initially, okay, we are making use of a thing here, because initially we know that initially it said that the pion is at rest, right? The pion is at rest. Okay, so finally also you should have p nu and p mu vectors, all right, equal and opposite. Okay, p mu vector, p mu. We should know the fact that p mu vector is equal to minus p nu vector, or p nu vector is equal to minus p mu vector. Okay, so this you can write this as m pi square c square minus 2m pi p mu c, right? Because of momentum conservation, right? Initially the particle was at rest, okay, and then they are going in opposite directions. Okay, now you just solve for p mu and you get the answer. Okay, you get modulus of p mu vector. I'll write a vector here just to distinguish it from the form momentum. So modulus of p mu vector is equal to, you just solve for this. You see that it's equal to, you take this to this side, so it becomes m pi square minus m pi square c square minus m mu square. Just, okay, you just solve this. All right, this is m pi square minus m mu square. There's a c square there, so you can cancel that c, and on in the numerator denominator is 2 m pi, right? So we've got p mu vector from this. Okay, now the small problem with this is that you have to do this in different ways depending on the problem. All right, for that you need a bit more practice. So in order to, so for example, we started with we first found the combination p nu equal to p pi minus p mu, and then we found the energy. Right, we used the same equation, but we wrote p mu equal to p pi minus p nu, and then we found the momentum. So you just need a little bit practice to see what equation exactly to use. Right, there are a few tricks that we can use in problems. Now we can easily find the velocity. You can easily find the velocity because you know that v by c square is equal to p. Okay, v mu by c square is equal to p mu divided by e. Right? We have got p mu, we have got e. You just divide and multiply by c square, you'll get the velocity. Right? This is p mu. So it is the velocity becomes, just divide it. All right. We already found the energy, so it's equal to m pi square minus m mu square from here. Okay, the 2 m pi thing will get cancelled, and from the energy you'll get an m pi square plus m mu square. All right, and then multiplied by c. Okay, so that's maybe this method is easier in some other problems. You just write down the form momentum equation, write it in the suitable form, and then square, and then you see that you can use all this invariance relations. All right, there's one kind of problem where this method is particularly useful. Right, we can make use of the fact that the momentum square is also invariant, relativistically invariant. All right, so we can actually go to a convenient frame and calculate this. Okay, if it's difficult in the given frame, we can go to a convenient frame and calculate this. And since this is invariant, we can always we always know that it's the same in all reference frames. Okay, so that is one way to do it. For example, sometimes we'll go to center of mass frame, what's known as center of mass frame, and calculate this. Right? But we won't spend too much time on this. We'll maybe I'll just put a few things in your notes. Okay, but for now we can, I think, stop with it. Okay, you can try other problems using this form momentum thing. You don't have to use this. You can always use the energy conservation and momentum conservation. Right? But if you are more interested, you can practice this using form momentum. Okay, now I think we can stop now. From tomorrow, we'll go to another section, or maybe do a couple of more problems, maybe one or we'll just go to, I just wanted to tell you that such a method exists. All right, you don't have to use it, but anyway. Okay, right now I think we'll wind up for today, and tomorrow maybe in the next class we'll start with the Doppler effect and then wind up special theory of relativity. We spent a lot of time on special theory of relativity, primarily because it's interesting and we have time, and also because such questions can be answered. All right, there are always questions from special theory of relativity. You know that there's a section on special theory of relativity in classical mechanics. There's also relativistic electrodynamics. Okay, so there are problems coming from relativity. We can solve these things. Okay, all right, shall we wind up now?
Okay, sir. Thank you.
Okay, thank you. Are there any questions? Is there anything that's not clear?
Fine, sir.